Welcome to our channel. Let's begin the journey.
Welcome back to The Explainer. Today, we are taking an intense, highly visual plunge straight into the microscopic realm. We're leaving the macroscopic world behind and digging right into the architecture of matter itself. Here's our roadmap for today. 1. The empty cathedral. 2. Discovering the neutron. 3. The language of nuclei. 4. Nuclear radius and density. And finally, 5. Mapping it all out on the chart of nuclides. Let's get right into it.
Section 1. The empty cathedral. Zooming into the atom.
We all know the baseline atomic structure, right? Extranuclear electrons buzzing around a dense central core, the nucleus, which is packed with positively charged protons and neutral neutrons. Now, those incredibly light electrons dictate the chemical behavior of the atom, sure. But today, we're ignoring them. Today, we are locking our focus strictly on that heavy central core.
Scale is where things get wild. We're talking about an atom that's roughly 10 to the negative 10 meters across versus a nucleus at a mere 10 to the negative 14 meters. So picture a massive, towering cathedral. If an atom were enlarged to be the size of that entire cathedral, the nucleus would be nothing more than a tiny pinhead sitting right in the center. The volume of the nucleus is basically 10 to the negative 12 times the volume of the atom, which means, what we consider solid matter is overwhelmingly, almost entirely just empty space.
And this isn't just theory. Ernest Rutherford actually proved it. He fired fast alpha particles, packing about 5.5 mega-electron volts of energy, straight at exceptionally thin gold foils. He found that the closest an alpha particle could get before the pure Coulomb repulsion bounced it back was around 4.0 times 10 to the negative 14 meters. That proved, without a doubt, that all the positive charge and pretty much all the mass is crammed into an unimaginably tight space. Section 2. Discovering the neutron. Solving the missing mass puzzle.
So Rutherford finds this tiny, dense nucleus, but then physicists hit a massive wall, a huge paradox. The mass of the nuclei they were measuring just did not match the electrical charge. If a nucleus had a specific number of protons giving it its positive charge, the actual mass was turning out to be double, sometimes way more than what those protons alone should weigh. So if protons provide the charge, where in the world is all that extra mass coming from?
Enter James Chadwick in 1932. He's bombarding beryllium with alpha particles and notices this really weird neutral radiation coming off it. And this stuff was actually strong enough to knock protons straight out of light nuclei like helium and nitrogen. By running the strict numbers on conservation of energy and momentum, Chadwick realized, hey, this isn't just regular radiation like photons. It's an entirely new neutral particle with a mass almost exactly matching a proton. Boom, the neutron is discovered. It was the missing piece of the universe's puzzle, rightfully earning him the Nobel Prize in Physics in 1935.
Section 3. The language of nuclei. A, Z, and N.
To really get into the mechanics of this empty cathedral, we gotta speak the language, the strict academic nomenclature. Think of Z and A as the keys to the kingdom. Z is the atomic number, just the number of protons. Z dictates the chemical element, plain and simple. Then there's A, the mass number. That is your total head count of protons plus neutrons, which we collectively call nucleons.
Which brings us to a super elegant but absolutely critical formula. N equals A minus Z, N being the neutron number. You take the total mass number, subtract the protons, and you get exactly how many neutrons are crammed into that little pinhead. And knowing that number, it's not just trivia. It tells us whether an atom just sits there totally stable or if it's radioactive and potentially dangerous. It's vital for identifying exactly what we're dealing with.
Section 4. Nuclear radius and density. Inside the pinhead.
Let's look at the math, because electron scattering experiments let us calculate exactly what's going on inside that pinhead. We use the formula where the radius, r, equals r sub 0 times a to the power of 1/3. A is our mass number, and r sub 0 is a constant, 1.2 times 10 to the negative 15 meters, or 1.2 femtometers. Because the radius scales with the cube root of the mass number, when you plug that into the volume equation for a sphere, 4/3 pi r cubed, the volume turns out to be directly proportional to the mass number, A. In plain English, nuclear matter is essentially uniform. Add more particles, the nucleus gets bigger, but the density stays exactly the same.
And what a density it is. If you run these numbers for an isotope like iron 56, you get a density of 2.29 times 10 to the power of 17 kilograms per cubic meter.
I mean, just wrap your head around that. That is staggeringly dense. We are literally talking astrophysical neutron star levels of density right inside everyday matter. Its mass compressed to its absolute physical limits. Section 5. The chart of nuclides, mapping the isotopes. Now, let's zoom out a bit and see how these crazy dense nuclei are organized across the universe. We have to talk about isotopes. These are nuclides of the exact same chemical element, same atomic number, same protons, same electrons. The only difference? The neutron number. You can tack on a neutron or take one away, which completely changes the mass and the nuclear stability, but leaves the chemical properties 100% perfectly identical. They're chemical twins, but physical strangers. Think about the extremes here. Take the lightest element, hydrogen. In nature, you've got light hydrogen with 1 proton, 0 neutrons. Add a neutron, you get deuterine. Add another, you get tritium. Chemically, all just hydrogen, but then go all the way to the heavy end with uranium. Uranium-235 has 92 protons and 143 neutrons. Uranium-238 has the same 92 protons but 146 neutrons. Those 3 tiny extra neutrons? That is literally the difference between an inert piece of metal and the highly fissile fuel that powers entire nuclear reactors. Now, you might be thinking, hold on a second. We're packing all these positively charged protons into a space the size of a pinhead. Shouldn't the electromagnetic force make them violently repel and just blow the nucleus to pieces? Well, yeah, it absolutely should. But it doesn't, thanks to the strong nuclear force. This cosmic glue completely overpowers the electromagnetic repulsion, binding those protons and neutrons together. But it only works at incredibly short femtometer distances. Which brings us to a pretty wild thought to wrap up this explainer. We've got this impossibly dense core locked together by the strongest fundamental force in the universe. So what happens when we intentionally force it to break apart? Well, that unleashes the staggering, world-changing energy of nuclear fission and fusion. And that is exactly what we're going to dive into next time. Thanks for joining me on this deep dive into the empty cathedral of the atom.
The view from here is breathtaking. Command, we are in position and ready for the next phase. If you liked the video, subscribe and comment the topic you want next. Thanks for watching, and stay unstoppable.